Okay, so I'll be talking about quickly generating random things. Okay, this is joint work with Andrew Arman and Jane Gao. And okay, so here's a random three regular graph. You can see every vertex has degree 3. And we want to generate one uniformly at random with the given number of vertices. Well, maybe not 3 regular, maybe we want to do D regular for arbitrary D. So each such graph with n vertices has the same probability. And the question is, how do you generate one? Or you can ask more generally, how do you generate graphs with a given degree sequence? And the methods we use for the regular ones tend to work pretty well for given degree sequences. So I'll just focus on the regular ones mainly. Okay, another problem is what's equivalent to a bipartite multigraph. A random matrix with non-negative integer entries such that the row and column sums are given. And they're also called contingency tables, if you like. Okay, so these problems, here's a brief history of the runtime for generating a random deregular graph anyway. In the 1970s, there were various results on counting graphs of given degrees that kind of inside them have this model you can look at probabilistically and generate graphs of given degrees at random. And they tend to give things like a deregular graph with a runtime that's exponentially d squared, which isn't so good if you want to generate a random, say you want to generate the complete graph with 10 vertices at random. You want a 9-regular graph with 10 vertices at random. It takes a long time to generate one at random using the model that comes from these results. Then with the previous speaker, Brendan, we got a result that showed how to generate a random deregular graph in time only in d cubed. If d is bigger of n to the 1/3. Well, that's not too bad, but if d is like 100 million, which some people want to generate graphs the size of the size of the World Wide Web, then that's still a bit slow. And sometimes you want to generate a whole lot of graphs also. So there is still some reason to try to get faster algorithms. Jane Gao and I much more recently found a way to extend this result to higher degrees, but the runtime was the same in d cubed. Okay, now I'm going to try to illustrate the new idea in that it's the basics of the idea of how you can get faster and quite a lot faster than these algorithms. It's not a big change from those algorithms. It's kind of like a trick you can do that changes part of that algorithm and makes it a lot faster. It's the crucial part. So I'm going to describe this thing, and first of all, I'll give a story about how it works, and then I'll mention how it works in the context of the deregular graphs. So the new idea is incremental relaxation, which you might think is something like this, but that's not the correct picture for incremental relaxation. It's something that's we got from, it actually came about almost by accident. We're actually looking at the contingency tables problem, and things happened a certain way there. And then we realized that they also work to help with the generation of random deregular graphs in the first place. So first of all, a story about, to give you an idea of what incremental relaxation is. Now, okay, so you imagine you have a boss. Your boss is a very demanding, sometimes angry, very angry, irritable woman who says, I want a 10 regular graph on 1,000 vertices generated uniformly at random. Okay, now your boss also has big boots. And so when she says she wants something by next week, you'd better do it, or she'll boot you out of your job with her big boots, and it won't be very pleasant. So, confronted with this, you wonder what to do. And then on the way home, a stranger gives you a graph that's a 10 regular graph on 100 vertices, whoops, but it's not uniformly at random necessarily. So what does the stranger give you? A graph that's 10 regular on 1,000 vertices, and it has an independent set, which I'll call an I set. Independent set S of size 10 that's been marked in the graph. Now, the stranger, who you can trust, because, well, in certain parts of Australia, you can trust all the strangers. Okay, so the stranger says that this graph, and together with the independent set, that pair of things is an object that was generated uniformly at random. Of all the graphs on 1,000 vertices, so they're 10 regular, and all the independent sets inside those graphs. That's a uniformly random ordered pair. Okay, so one idea is to give your graph to your boss. Give the graph that the stranger gave you to your boss. Okay, you can try that. There is a problem with it though. Okay, the problem is the probability of that pair, let's say it's 1 over n. Well, it'll be 1 over n if n is the number of possible pairs GS, where G is a graph that's 10 regular on 1,000 vertices, and S is an independent set in G. All right, so the probability that the boss gets given the graph that you give the boss is some function divided by n, where the function is just the number of independent sets in the graph of size 10. Okay, every graph occurs with probability proportional to the number of independent sets it has. Okay, so it's not uniformly at random. It's not constant divided by n. Okay, we can fix it. We can use a standard method to fix that. We can flip a coin where the probability of heads is p. Okay, and set p equal to this number here. It depends on f10. Now the probability was f10 over n. And then with probability p, you give the graph to the boss. Otherwise, you throw away the graph and you hope to meet the stranger the next day on the train and get another pair of graphs with an independent set. Okay, well, after doing that, the probability that the boss actually gets the given graph G is the probability that the stranger gave it to you times the probability that you retained it and passed it on. And these things cancel, of course, and you get a constant number that doesn't depend on the graph. So that graph is given to the boss uniformly at random. Every graph has the same probability of being given to the boss. It's a form of, just a simple case of rejection sampling. You have unequal probabilities and you equalize them. Okay, but there's a couple of things you've got to check. That's the probability that you keep the graph and don't throw it away. But what if the probability is greater than 1? Well, it's pretty easy to check that f10 is at most, if at least, this quantity here divided by 10 factorial. F10 is the number of independent sets of size 10, and you can get one greedily by choosing a vertex, then choosing another vertex that's not adjacent to it in at least that many ways, then choose another vertex not adjacent to those two, and so on. Okay, so anyway, f10 is at least, it's greater than 900, choose 10. You can just check it easily. But there's another problem. If the probability P is extremely small, it might take many days to success, and you won't have your graph by next week because you can only meet the stranger once a day. Okay, so if P is extremely, well, we can actually check that P is not extremely small though. It depends on how big F10 can get. But F10 is at most 1,000 choose 10, the number of independent sets in the graph is trivially at most 1,000 choose 10. So the P is at least this thing, which is around 1 over E. So probably by next week, you'll be able to get a suitable graph to pass on to the boss. All right, is that all clear? Are we fine now? Well, there's one other problem. We've only got a week. How quickly can we compute F10? F10 was the number of independent sets of size 10 in the graph that the stranger gave you. How do we compute it? Well, you might think it's easy to count independent sets of size 10, but maybe it's not so straightforward. If you use an exhaustive search, you might, exhaust all the number of ways, just exhaustively search for all the independent sets, then you might find that you have a very slow algorithm and you don't get finished in a week. Now, there's a naive idea that, well, pretty naive, that lets you use inclusion exclusion, and you can get start with all the possible subsets of vertices, throw away the ones that have some edges between them, use inclusion exclusion to make sure you count every independent set exactly once. There's a standard way to do that, but there's a lot of programming or whatever to do if you do it in a very naive way. And it's still not that fast. It takes a while to write the program. Maybe you haven't got a whole week. So maybe you've only got a week. Maybe it'll take the whole week to write the program. Okay, so this incremental relaxation solution completely avoids actually computing this number. You don't have to compute it. You can still start with the ordered pair GS and end up with a uniformly random G. How does it work? So suppose you're given a G, I'm calling it GK, if you have a graph, the graph G, the same graph G, and there's a distinguished independent set of size K. And let's suppose that's generated uniformly at random as an ordered pair. So every pair G, comma, set of size K, every such pair is generated uniformly, it's generated with equal probability. We say G is anchored at the independent set. Okay, for example, with 3 vertices, I'd represent it this way. It's similar to what Brendan did. The dashed lines represent things that are not, they're absent from the graph. So we just have 3 vertices and a few edges are missing, or specified to be missing. And now we want to produce, that's a GK with K equals 3. We'll keep running with that example. We wanted to produce a GK minus 1 uniformly at random. We start with the G10 uniformly at random. We want to go to G0. Now we can relax the anchor by removing VK from the picture. Just delete that and you'll get a thing anchored at 1 less vertex. Okay, what happens when you do that? If there are n possible GKs, the probability of GK occurring, remember that's just like that's an independent set of size K specified in our graph, G. Then the probability of GK occurring is 1 over n. Now, if we just use the graph with the 2 vertices, then the probability of obtaining that graph just by forgetting and not doing anything else, the probability will be, again, a function which tells you the number of valid choices of the 3rd vertex, B3, divided by n. So if you have this graph, the probability it occurs is the number of ways that it could have come from something with a V3. Okay, so what we do is use rejection sampling, accept the graph with just 2 vertices specified with probability equal to this. And all we need for this to work is like the previous example. What we do is we, the probability that we generated the pair, the graph with the pair, the specified pair, the probability we generated and accepted it is the product of these 2 quantities, and the f's cancel and we get a constant. Okay. You can ask, can P be bigger than 1? Well, it's easy to check it's not. Can P be very small? For similar reasons to the previous argument, it won't be very small. And how do you compute this number, F? That was the difficult thing last time. Well, it turns out to be easy. If you're given V1 and V2, and you want to decide how many ways you can have a V3 that's independent of those two, you can do it by considering all possible vertices and throwing out the bad ones, which are the neighbors of V1 or V2. And to count those takes time order G in this case. Very quick. Okay, then you get that gives you a random GK-1. It's a copy of G anchored at an independent set of size K-1. Okay. Okay, so I just started just checking something. So this, you can repeat it, of course, for a K-2 down to G0, which means that in the end you get a random, uniformly random graph, G. Okay, so that makes the boss very happy, and you can easily do that and be quite likely to succeed by next week. Okay, how does that work for D-regular graphs? For random D-regular graphs? Well, there is a black box, which comes from the pairing or configuration model, those enumeration results in the 70s. And out of that box comes, we can assume by some simplifications that we can get a D-regular n-vertex graph, a multigraph. The trouble is it's not a graph, it's a multigraph with no loops, no three edges in parallel, and it's uniformly random, conditioned on the number of double edges. So you know that all the graphs with a given number of double edges occur with equal probabilities. Now I am oversimplifying, but this is just more or less, this is the heart of the problem. Now we know that the number of multiple edges is highly likely to be order of d squared. And we basically want to get rid of them. The way that Brendan and I got rid of them in the 90s was do the switching. You have this configuration with a double edge. You choose two other edges at random and just replace those four edges by two paths, which naturally won't have any edges between them because you rip them out and put in new edges. Now that's just an anchored graph. A graph with two paths specified, and it's uniformly random, which this one was uniformly random, which is the output of this box here. That's uniformly random. Then this guy here is a graph with usually with one less double edge than it started with, and but there are two paths specified. So it's anchored at a pair of two paths with these forbidden edges, three forbidden edges. Now, what we did then is de-anchor this thing by incremental relaxation. Here, instead of removing one vertex from the independent set like we did before, we remove one two-path. So we go to something anchored at a single two-path, and you just have to say, well, how many ways are there? What you need to compute now, the difficult thing up here would be to compute how many ways you can go backwards in order to do rejection sampling. How many ways, given one of these, a graph here, how many ways could it have been created by one of these operations? And it's basically pretty complicated. But by incrementally relaxing, we get a much simpler problem. And we can basically do it in by an inclusion-exclusion, where we count all the two paths in the graph and then throw out the ones that are bad, that have any edges, any forbidden edges, or the ones that collide with this path here. And it takes a little bit of care, but you can do all this. This happens to be the hardest bad case, where you have another two paths with a couple of edges involved that are bad. But after a few sneaky tricks, you can do all this in time order d squared for one step of one switching in order to decide whether to reject or not. Okay, so then there's a second step of de-anchoring, which is relax this thing, which is even easier. I don't even need to talk about that really. You're just seeing how many, you're given a graph and you want to know how many two paths there are that have no multiple edges in them. It's actually a multigraph, remember, it's got some order d squared double edges in it. Okay, so you do this step and you do another switching to remove another double edge and so on. all along the way you do incremental relaxation, or you do rejection samplings to keep the result a uniformly random thing with a given number of double edges. So in the end, the time taken per double edge is order d squared. That's as long as you did an appropriate, when you're generating the pairing, you set up some appropriate data structures at the same time. The pairing, the black box, that is, the black box, generating the multigraph in the first place. That takes time order nd. Okay, so this is d squared each time. The number of double edges was around d squared over 4. So the time taken to get rid of all the double edges is around d to the 4th. Okay, so for the time complexity, it's d to the 4th plus the original big O of nd. Okay, so just as a summary of what we have there, then what that gives us is time nd. That's order of the time taken to write the graph down. That's how quickly we can generate the deregular graphs with d as big O of n to the 1/3. In that case, the d to the 4th is also big O of order dn, or big O of dn. If you have an arbitrary degree sequence with maximum degree m to the 1/4, where m is the number of edges, now that's a typo in the abstract at m to the 4th. It's actually m to the 1/4. So if the max degree is order m to the 1/4, then again it's linear time, order m, where m is the number of edges. If we do deregular graphs of higher degree, then we get this result. This is up to root n, size root n. Jane, Gao, and I did this first in time d cubed n, and then now it's changed down to dn plus d to the 4th, which is almost linear. It's just got this extra d to the 4th term. Power law graphs, we have a result for that, which used to take time bigger than n to the 4th. I won't go into what the definition of that is. That's for people who know about it. The parameter is bigger than 2.88 for our result to work. And now that's again a linear time algorithm. And by the way, all these results have now been implemented in programs that you can get. Well, you can get the first 3 of them are on my webpage, and the 4th one is in a master's thesis that will come out fairly soon, I guess, in Germany. That's the implementation of it. Finally, contingency tables or bipartite multigraphs, as long as the maximum degree is not very big, we get again a linear time algorithm for generating those. Okay, even, a fully polynomial approximate uniform sampler was not even known for all the cases that we've covered here. So this is a better result than was known before in several ways. Okay, that's about all. Thanks, that's the end. Thank you.
Thanks, our speaker. So do we have any question? So how you come up with the term incremental relaxation? Did you hear it before?
Okay, so you relax the constraints, right? That was the first way I was thinking about it. You have constraints on the graph. You have a graph that satisfies, when a graph is anchored, the graph satisfies certain constraints. And what we're doing when we de-anchor part of it is we're relaxing some of the constraints. So we keep relaxing and relaxing and relaxing. So we do it. The big point is you don't relax them all at once. If you relax them all at once, you have to count how many ways you can have a complicated subgraph in the graph. But if you relax them one at a time, then you just have to see how many ways you can extend. You can add a new constraint to the graph. So it's done incrementally. The relaxation is done incrementally. Whereas the old algorithms did the relaxation essentially all in one go.
All right. There is a question in the chat. Can you see it, Nick?
given marginals, was there no polynomial algorithm known? We don't have much on the contingency tables. We don't know of much that actually did. If you ask about exactly uniformly randomly generating, then we couldn't find anything in the literature. The only things would come for the case that there are bounded. Well, no, even for bounded degrees. So there have been some results on approximate generation. I didn't have time to talk about those, but there are a few results on generating things approximately uniformly. For instance, and there is an FPOWs that works for fairly low degrees and also for high degrees, but even the low degrees doesn't cover everything that we cover here. So it's just sort of a little bit of a mismatch. But the thing about those other results is they don't generate exactly uniformly at random. And what the heart of this sort of work here is to get things exactly uniform.
Hi, Nick. Exciting to me, who's worked on these problems for a long time. And one of the things that we sometimes need in statistics is generation of graphs with given degree sequences, but from non-uniform distributions, things like the hypogeometric distribution. And I wondered if you had thought about whether your algorithms can be adapted to non-uniform distributions. That's one question. And another is the question about three-dimensional arrays, you know, row, column, and line sums, which seems to defeat many things and seems hard for us to. So those are two questions.
Yeah, there are two questions. I've thought about high dimensional arrays. We've had a bit of discussion about that, but I forget which problem it was in connection with, whether it was this one or actually another one. So I'm sorry about that. I can't. It's obviously pretty complicated. But the first thing about hypergeometric distribution, so the graphs have different distributions depending on what?
Oh, saying not for graphs, for contingency tables.
Oh, for contingency tables. All right. Yeah, right. So that's where the marginals are not specified.
So the margins are fixed, and there's something called the multiple hypergeometric distribution that Fisher used, and we have a. There's a paper that lays it all out in some generality with Bernd Sturmfels that's called algebraic algorithms for generating from random exponential families or something. But there is a there's lots of special cases where we need your help, is all I'm trying to say. And
maybe we should talk about that sometime.
Right.
Yeah. Right. Thanks. Yeah, I haven't thought about it.
Yeah. Yet.
A comment and a question. In the case of three-dimensional arrays, one can count lines or count planes, and one of those, I forget which, actually gives you Latin squares if you have all the sums being 1. So nobody knows how to asymptotically count them, even in that simple case.
Slides.
The question to Nick, in the case of the contingency tables, are they square, or what happens if they're extremely non-square?
I know, yeah, they can be fairly non-square. Yeah, I forget the constraint. Yeah, there are constraints on them, but they're not square. They're just bipartite, equivalent to bipartite graphs. You know, there's some range of parameters that you can have for the two sides, the numbers of vertices on the two sides. So the row and column numbers can be varying.
Okay, thank you.
Yeah.
There is one more question in the chat about polytime algorithm for contingency table. Do you want to comment on that?
Oh, I see. Polynomial time algorithm for 0, 1 contingency table with given marginals. So that's like a bipartite graph. So 0, 1 meaning only 0 and 1 entries. Entries are all 0 and 1. So that's like a bipartite graph, and so we have so there will be I guess we didn't write it down explicitly, but the certainly in the paper with Brendan in 1990, we explicitly described how the algorithm works just as well for bipartite graphs. So the things you see here will work for bipartite graphs with the same sort of bounds on degrees. And there would be more or less, okay, so they work more or less like this because it depends on what the ratio is between the number of rows and number of columns. But the total, when you see a bound on the degree here, that would be a bound on the marginals for the contingency tables. So this one here, in fact, when we do this, for this algorithm, we start with the 0, 1 case. And we get that from the known results from before. But again, the degrees or the marginals have to be not very large compared to the total of all the entries. Actually, so for this one here, we get one of those 0, 1 matrices, and then we add the 2s and 3s in it. Well, there's not very many 2s occurring. This is so sparse that you don't get very large entries.